Hi, in this video we're going to be discussing our CS2100 tutorial 8 questions. Okay, so in these questions we have a mix of topics. The first two on K-map, and after that on we're going to revisit our MIPS processors control unit, and finally we're going to talk about enhancements that we can make to the processor architecture and to improve the overall performance of the system. Okay, so the first question is on K-map. For this question, we are going back to the K-map that we derived for the divide by 3 circuit from tutorial 7. Okay, so for this, basically, I have seen how we can do the simplification using Boolean algebra. Okay, and we saw that it was quite a painful process and very tedious. Okay, whereas if you use K-map, it's very easy. Okay, so let's see how we can use K-maps. Okay, so with K-maps, basically what you need to do is we need to have the size of the K-map that corresponds to the number of variables that we have. So since we have 4 inputs, we have a 2 by 2 K-map. So what you need to do is to write the variables here, A, B, and C, D here. Okay, subsequently, of course, you may have been taught different techniques. Okay, but I'm just going to show you one technique that I use normally, which is just put the different combinations here, 0, 0, 0, 1, 1, 1, 1, 0. Same thing over here. And of course, the important thing of K-maps is every column or every row, the bits, only one of the bits will change. Okay, so you cannot have an adjacent column or adjacent row where 2 bits are changing. Okay, only 1 bit changes from one row to another row or one column to another column. Okay, so once we do this, okay, so now we are going to put in the variables for x. Okay, and since for K-map, okay, so for now we're going to just focus on the minimum SOP expression. So we just focus on the ones. Okay, so for x, we can see that the ones are all here, 1, 1, 1, 1, and so we can do a grouping. So when we do a grouping over here, okay, the simplified expression, basically what you need to look at is in this grouping. Okay, so first let's revise quickly on the rules of grouping. The groupings must only be done in powers of 2. So you can group in as 1 element, 2, 4, or 8. Okay, and if you group only 1 element, then all the literals still remain. If you group 2 elements together, okay, then one of it can be eliminated. If you group 4 together, 2 of it can be eliminated. Okay, so for example, in this case, I have a grouping of 4. That means from A, B, C, D, 2 of them will be eliminated. So what will be eliminated are those that are changing in this group. Okay, so you can see that in this group, C and D continuously change. So what is remaining is A, B. Correct? So the answer is, for this simplified expression for x is equals to A dot B. Okay, so that is the final answer for x. Okay, now let's look at for y. Okay, so let's look at y. Okay, so again for y, I'm going to do the same thing. I'm going to first do a labeling here, A, B, C, D. Okay, it's good to put the labels here on the variables. Okay, so that you do not get mixed up. Okay, because it's okay to write it either way. Okay, but you must make sure that you translate from the truth table to the K-map correctly. Okay, so again I'm going to write 0, 0, 0, 1, 1, 1, 1, 0. Same thing over here. Okay, now I'm going to fill up the ones. So I have 4 ones here and 2 ones here. And in terms of grouping, okay, so we can see that these two will form a group, and within this two group, okay, like I said, when you group 2, one of the elements will be eliminated. So the one that eliminates this eliminator is the one that is changing. Okay, so within this group is in the same row, so A and B does not change, so it will be A bar B, okay, because 0, 1. And within this group here, C is constant and D is changing, so C remains. Okay, so that is how you get A bar B C here. And for this group over here, again, let's see what we get. Okay, so what we get is this is a group of 4, so 2 elements get eliminated, and since it's one whole row, that means C and D are continuously changing, so what is remaining is AB. So A B bar. Okay, so that gives us our final answer, which is y equals to a b bar plus a bar b c. Okay, so that is your final answer for y. Okay, so now let's look at the z variable. Okay, so again I'm going to label it first. So this is for z, this is ab, and this is cd, and I'm going to put in the 0 0 0 1 1 1 1 0. Same thing over here. Okay, now I'm going to put in the ones. So you have more ones here, one here, one here, and one. Okay, so now let's see how we can do the groupings. So for example, over here, these two groups, these two ones here, I can group them together, and this will be a bar b. Okay, let me just change the color here so it's easier to follow. So this is, so in this group, AB does not change, so it is A bar B. And in terms of the columns, D changes, so only left is C, so it is C bar. So A bar B C bar. Then what else do I have here? So over here I can have one group. Okay, and for this group I can call it so again this is a row, so the A and B does not change, so it's A B bar, and within these two columns C changes but D remains, so it is D, A B bar D. Then again for these two ones here, if I group them together, what do I get? I get again the AB does not change, it's the same row, so it is A B bar, and within these two columns D changes, so D is eliminated, so left is C, A B bar C. Okay, then I have these two ones. Okay, and these two ones can be grouped, okay, as so in this two ones is a column, so for the column C and D remain, and in terms of the rows, what changes? B changes, so B is eliminated, left is A, so A C D. Okay, so for this one over here at the top here, what can we do is I'm going to just use a different color so you can see it clearly. What we can do is we can actually group it across, so we can wrap around the K-map top to bottom, left to right, or all four corners. Okay, so I can actually do a grouping this way with this one over here. Okay, so this grouping here will be allowed because you're allowed to do a wrap around. So in this case, since it's the same column, so C and D again remain, and A changes, so left is B, so B bar CD. Okay, so the final expression for Z is A bar B C bar plus A B bar D plus A B bar C plus A C D plus B bar C D. Okay, that is your final expression for your Z. A bar B C bar, A B bar D, A B bar C, A C D plus B bar C D. Okay, so as you can see, with K-maps, it is a lot easier and a lot more faster. As long as you follow the rules of the K-map, you will get the most simplified expression as your final answer. Okay, so it's a much more easier and straightforward approach compared to trying to use Boolean algebra. Okay, now let's go on to question 2. In question 2, basically we are given a BCD. What is a BCD? A BCD code basically is a binary coded decimal. That means only numbers 0 to 9 are valid, and anything from 10 to 15 are invalid. Okay, so since they are invalid, we can put a don't care, okay, as the output, okay, for these input combinations. Okay, so in a logic system, when we say that these inputs are don't care, we can assume that either these inputs will never occur, or even if they do occur, we don't need to care about them, okay, because they are invalid. Okay, so that is why we don't need to worry about them being part of the input at all. Okay, And so in this question, we're going to see how we can actually make use of these don't care conditions. Okay, so we are given this 4-bit BCD input, and the output is actually P, which is a parity bit. Okay, and what is a parity bit? A parity bit is an additional bit that is added for error checking purpose. Okay, uh, so this parity can be odd or even parity depending on the nature of how we want to implement it. So if we look at this rule here, what we are told is if the current number of ones is already odd, then P is 0. If it is even, then we put a 1. So what we are saying is what we want is an odd parity scheme. That means eventually what we want is to have an odd number of ones, okay, in the whole packet. Okay, so before we go into the details of this, let's look at the truth table first. Okay, so if I look at the first entry 0000, so the number of ones is even number because it's 0, so I put a 1 so as the output P. So if I look at this whole 5-bit data packet right now, this has now an odd number of ones. Okay, so if I look at the next entry 0001, that I already have an odd number of ones in my XYZW, so P is now a 0. Okay, and so on. Okay, so you can sort of follow this rule to implement it or to figure out the rest of the P values. Now, how do we use this parity scheme? Okay, so for example, okay, uh, if I have a transmitter sending data over to a receiver, okay, if the transmitter is sending this first or this second data packet 00010, then and we know that both of them are now operating on the odd parity scheme, what I expect to receive over at the receiver side is also 00010. But what if I receive 00011? Okay, what if I receive this? Okay, then where at the receiver side, what will happen is the receiver would actually be counting the number of ones in the whole data packet. And since it's supposed to be operating on odd parity, if I see that I eventually have an even number of ones, then something is wrong. Okay, that means some data has been corrupted. Okay, then I discard this packet. Okay, so I say that this is an invalid packet. But what if, okay, so of course that is the general use of this parity scheme. But imagine that right now if I have a double bit flip 01011, okay, that means what has happened is this bit is also flipped and this bit is also flipped. And now when I look at the total number of ones, it is an odd number. Okay, and so the system will accept this even though it is wrong. Okay, so you can see that this error checking system is not a very robust scheme. It's a very simplistic and basic scheme that you can use, okay, for very low cost systems. Okay, but in generally we have a lot more complex error checking mechanisms that you can probably learn in some other modules relating with network and data packets. Okay, but this is a very simple basic scheme, okay, for error checking. Okay, now coming back to our question on parity, we can see that this is how we have completed the truth table. And now what we're going to do is we are going to implement the K-map to get the SOP. Okay, so let's do the SOP first, and then we will look at how to do the POS. Okay, so in this question, it's supposed to do both. Okay, so I'm going to do as before. So this output here is P. Okay, and my inputs are X, Y, Z, W. Okay, and I'm going to do what I did before 000111110 0011110. Okay, and let's put in the ones. So the ones are here 1 1 sorry 1 1 1 1 X X X X X X 1. Okay, so these x's here are the don't care conditions. Okay, you can put it as D or put it as x's, as up to you. Okay, so these x's or don't care conditions, how do we use them? Okay, so the main idea is we want to use them as long as it helps us to get a more simplified expression. Okay, we do not need to use all of the x's. Okay, we don't need to use all of the x's. As long as it helps us to get a more simplified expression, then we use it. Okay, so for example, if I look at this one here, I can do a grouping of these three x's beside to get a group of 4. Okay, and this group of 4 will now give me a expression of x w. Okay, because this row to this row, x is constant, y changes, and this column to this column, z changes, and w is constant. So I have xw. Okay, and now what else can I use the x's for? So you can see that this one can be now paired with this x over here. Okay, so this will give me an expression of so since it's a column, so the column values remain, uh, and the row I can see the x changes, y is constant, so this y will remain. Okay, similarly I can do it over here. Okay, and for this, what do I get? I get again the column values will remain, so it will be z bar w, and then in terms of rows, x changes but y remains, so y is there. Okay, how about this one over here? Again, what I can do is I can do a wrap around this with this. Okay, I can do a wrap around, and with this wrap around, what do I get? With this wrap around, I can see that the z and w, since it's the column, it remains, and the x changes, so left is y bar z w. And finally, I have this one here. Okay, this one, as you can see, I cannot pair it with anybody because there are no x's or ones to the right or below or it. And if I try to wrap around also, there is nothing over here or nothing over on this side as well. So there's really nothing I can do for this single one. So I have to group it as a single grouping. So what I have left is x bar, y bar, z bar, w bar. Okay, so the final expression here for P is given by x bar, y bar, z bar, w bar plus y z bar w plus y z w bar plus x w plus y z bar w. Okay, so that is the final expression for the SOP. Okay, for this truth table here. Now, the next part of the question asks us to use K-map to use POS. Okay, to use POS. Now, how do we go about doing this? Okay, again, you may have seen different techniques in class or whatever, or online. Okay, I'm just going to show you one technique that I generally use. If you have another approach, then you can also try that, no problem. So for a POS, what we do is we look at the zeros. Okay, we group the zeros in the K-map. Okay, so let's look at the K-map again, but this time instead of focusing on the ones, let's focus on the zeros. Okay, so let's write it first. So this is P, this is X, Y, Z, W. Okay, so 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 1, 1, 1, 0. Okay, and then let's now focus on the zeros. So the zeros are here, zeros, 0, 0, 0. The x's remain where they are. Okay, and I have one more 0 over here. Okay, now that we have all the zeros there, let's do the grouping. Okay, let's do the grouping first, and then we will see what we can do with the groupings. Okay, now coming back to here, what we can do is, for example, here this x0 and this xx, we can actually do a wrap around. Okay, so by doing a wrap around here, what do we get? We get x and W bar. Okay, X W bar. Then this 0 and this X we can group together over here, and this gives us Y Z W. Okay, this 0 and this X we can also group together, and that will give us Y Z bar W bar. Okay, then we have another wraparound here, this 0 and this X over here. Okay, and this would give us Y bar Z W bar. Okay, and again, as before, we are still left with a single 0 over here, which cannot be grouped with anybody else. Okay, so for this grouping over here, what you have is you still have the X bar, Y bar, Z bar, and W. Okay, so now that we have done the groupings for the zeros, how do we proceed to get the POS? Okay, so the way to go about doing this is to understand that since we are grouping the zeros, this min term expression is actually an expression for P bar, not P. Okay, so I'm going to write it as a min term expression, but now this is actually a P bar expression. So it is X bar, Y bar, Z bar, W plus Y, Z bar, W bar plus Y, Z, W plus Y bar, Z, W bar plus X, W bar. Okay, and once we do this step, in order for me to convert this into a POS expression, I use the De Morgan's theorem, which basically says I put a bar on top here and I put a bar on top here. So from that, what I'll get is P double bar is P. Okay, and now what I have is X bar, Y bar, Z bar, W. So now I am applying the De Morgan's theorem to all the SOP terms here. Okay, so once you complete this step, okay, you can see that it is actually quite easy to relate SOP and POS directly from your K-map. So I'll get X plus Y plus Z plus W bar, Y bar plus Z plus W, Y bar plus Z bar plus W bar, Y plus Z bar plus W, X bar plus W. Okay, so that is your final POS expression for your given truth table and K-map. Okay, so this is the technique that I use. If you think that you do not want to use this approach and you can just directly translate from this grouping into this final answer, also go ahead. Okay, no issues. I'm just showing you a systematic approach to solve these questions. Okay, now another important thing that this question is asking is for us to sort of analyze the relationship between the SOP and POS over here. Okay, now if I were to look at SOP and POS, if the truth table that I have, okay, if the truth table that I have does not have any don't care conditions, that means they are all ones and zeros, then the SOP and POS will be direct complements of each other. Okay, which means that a circuit that I produce for SOP or the circuit that I produce for POS would behave exactly the same way. Okay, but now that I have don't care conditions, what happens? Okay, what happens is there's a possibility that some of the don't care conditions are interpreted differently in the different K-map reductions. Okay, so one example you can see here is this bit here, which is the 1111 bit. Okay, so you can see that in this SOP expression, this 1111 input is interpreted as a 1 to help me with the reduction, whereas in this POS, this 1111 entry is interpreted as a 0 to help me with my reduction. So since both of these K-map reductions has interpreted this input as different logic levels, it means that the circuit that I eventually build will be different and they will no longer be direct complements of each other. Okay, so they are both logically correct, but they are no longer direct complements of each other because we have interpreted them differently in both these situations. Okay, for question 3, we are basically revisiting our favorite MIPS processor, and now we're going to focus on the control unit. Okay, so as we have seen before, the control unit is responsible for generating all the control signals that will be used to channel the flow of information through the processor as it is executing an instruction. Okay, and though we have a 6-bit opcode, okay, for this first part of the question, we are going to just focus on a simplified version of the opcode, which is only 4 signals. And using these 4 signals, we are supposed to generate, okay, the register destination and register write signals. Okay, how do we go about doing this? Okay, so let's just fill in the truth table first. So here I have 1, 0, x, x here, and 1, 1, 0, 0 here. Now, let's look at register write first. For register write, you can see that it is quite straightforward, that it is 1 as long as it is a R-type instruction or load word instruction. So I can say that register write is equals to is R-type or is load word. Okay, so as long as the is R-type or is load word is 1, then the register write will be set. Now, how about register destination? Register destination has 2 axes here for store word and BEQ. And what we have seen before is the access or don't care conditions can be interpreted in a way that makes our life easier. Okay, so if it helps us, then we interpret it and use it to our advantage. Okay, if not, we don't need to use it. So right now, this access we can interpret them as either 0, 0 over here or 1, 1 over here. Okay, if I were to take the first option here of interpreting it as 0, 0, then I can easily write that register destination is equals to is R-type. Okay, or if I take the other option here of putting them as 1, 1, then I can also say the register destination is equals to is R-type or with is store word or with is BEQ. Okay, so that is one way of interpreting it. The other way of interpreting it is instead of looking at the ones, you look at the zeros. So we know that register destination for this combination only load word is 0. So I can say that is also the complement of the is load word bit. Okay, so both of these are logically correct. And is of course the second option is easier to implement because you only need a single NOT gate, whereas here you need to have a 3 input OR gate. Okay, so in terms of implementation, you could say that this second option is easier and cheaper to implement. Okay, so that is for part A, where we are generating control signals using these 4 simplified signals. Now in part B, what we are going to do is we're going to explore using all the 6 bits of the opcode to generate the appropriate control signals. Okay, how do we go about doing this? Okay, so what we do is we already have these opcodes from our MIPS instruction set. Okay, and now what we're going to do is we're going to use all 6 bits to generate the appropriate signals. Okay, so to do that, you just write out all the bits here, op5, op4, op3, op2, op1, and op0, and you draw these lines across. Okay, so what we're trying to do is we're just trying to channel out all these lines. And if you look at R type, for example, all the bits must be 0. So I can say here must be 0, here active flow. So all these bubbles are to indicate that they are active flow inputs. Okay, to an AND gate here. And this is your R type. For load word, is basically again the same thing. You follow through. So for example, load word bit 5 here must be a 1. 432 must be a 0. 0. So whenever it's a 0, it becomes active flow input to the AND gate. And then 1 and 0s are 1. Okay, so similarly, you can follow through this approach, okay, for all the other control signals. Okay, so that is one way of going about and approaching this question using the 6-bit opcode. Right now, I'm going to discuss another option where instead of using all the 6 bits, you can try to use the least number of bits possible to generate the control signals. Okay, for this, basically what you can do is you can use what we call I power, okay, to observe unique patterns in the control signals that do not appear in the other instructions that we are trying to decode. Okay, so what do I mean by this I power? So for example, if I look at R type is the only instruction where bit 5 is 0 and bit 2 is 0. Okay, so I can say that bit 5 and bit 2 both 0 or both active low will generate the is R type signal here. The R type signal here. Similarly, you can see that for load word, it is when opcode bit 5 is 1 and bit 3 is 0. Okay, so if I say op5 and op3, okay, this would be your load word instruction. Okay, for store word, you can see that it is the only instruction where bit 3 is set to 1. Okay, so looking at bit 3 alone, I can say that is my store word. Okay, and looking at bit 2 alone, I can say that is my BEQ. Okay, again, why does this work? Because this works only if there are no other opcodes to consider. Okay, so let me repeat that. This approach to look at unique patterns for the instructions, okay, to generate the appropriate control signals only works if there are no other 6-bit opcodes in the system. Okay, if there are other opcodes to consider, then this approach does not work. Okay, if there are other instructions where I need to factor in, then I still need to go back to using the 6-bit opcode as we saw earlier. Okay, this approach works, or this simplified approach works if there are no other instructions. Okay, so this is one way of taking the same 6-bit opcode, but instead of looking at all 6 bits, I just look at I look at the least number of bits to generate the appropriate signals that I want. Okay, so that wraps up question 3. For question 4 is about applying Amdahl's law on understanding the overall improvement that we can make in a system. Okay, so the first part here, okay, we are told to analyze whether any one of the enhancements can speed up the client's code. Okay, so in the comic strip that you have, basically what we are trying to do is we are trying to improve the either multiplication by 8 times or make the division, improve the division by 5 times. So how do we go about doing this? So if I look at the speed up for multiplication, okay, so the way to go about doing it is 1 over, so the multiplication itself takes up 50% of the time, so that is 0.5, and that 50% of the time is now improved by 8 times, okay, and what is remaining is another 50%, okay, besides the multiplication. So that gives me 1.78, which is a 78% improvement. Okay, now if I look at the speed up of the division, again, how do I go about doing it? Division takes up 20% of the time, so 20%, and this division is increased, performance is increased by 5 times, okay, and the remaining after 20% is 80%, so that gives me improvement of 19%. Okay, now if I were to combine both the multiplication and division improvements, okay, the overall speed up, okay, for both would have been 1 over the multiplication, which is 50%, improved by 8 times, plus the division, which is improved by 5 times, plus whatever is remaining, so 0.5, 0.2, so remaining is 0.3. So that will give me 2.48, which is 148% improvement. Okay, so you can see that adding or implementing both the multiplication and division improvements, then I get an improvement of more than double. Okay, just one of them alone does not give me the desired improvement of 2 times speed up. Okay, so that is your question 4, which is on Amdahl's law and the speed up measurement technique. Now for the last question, which is looking at CPI. So we are given this following information, okay, where we have a processor executing a code, and this code has a mix of instructions as shown here, and we are given the percentages of this type of instructions together with the number of cycles that it takes to execute each type of instruction. So as you can see, this integer multiply is a expensive operation because it takes 10 cycles to execute. Okay, so as much as possible we want to avoid this integer multiply. Now the first part of this first part A of this question, we are computing the overall CPI, cycles per instruction of the processor, and basically what you need to do is, you for each of these entries here, you take the percentage multiply by the number of clock cycles, so 0.25 multiplied by 2 and so on, and you add up everything together as shown over here, and you get the CPI as 2.3. That means you take an average of 2.3 cycles per instruction, okay, for this processor. Now in part B, basically we are focusing on this integer multiply, okay, and we know that a multiplication can in fact be replaced with a possible shift and add, okay, because if I can replace that multiplied number by a number that is a power of 2, then I can do a shift, okay, which is this, and then followed by add operation here. Okay, now this shift and add obviously is going to be much faster than the single multiply alone. Okay, and now what we are given is that half or 50% of all the integer multiplications can now be converted into shift and add operations, and one multiplication instruction is equivalent to 3 shift and add operations. Okay, and now we're supposed to compute the new CPI. Okay, so first thing is, now that half of the multiply instructions are converted to shift and add instructions, the overall number of instructions is now going to go up, correct? Because now each multiply instruction is equivalent to 3 shift and add instructions. Okay, so I need to calculate this new overall percentage increase in the code size. So since 50% of the multiply instructions are converted, the other 50% is not converted. So 2.5% is converted and 2.5% is not converted. So whatever that is converted, I subtract from here, and that has to be replaced with 2.5 times 3. Okay, why 2.5 times 3 is because each instruction is now replaced by 3 instructions. Okay, so the overall size of my instruction is now increased by 5%. So if my overall code size has increased by 5%, then I need to recalculate all the percentages of the different type of instructions. Okay, so once I do this, so this is the important step that most students will miss out. And once I do that, I can calculate the new CPI. So again, it's the same thing. This multiply by this, and this multiply by this, and so on. And after that, you add up everything. Okay, so that is your new CPI. And now the speed up has to be the based on the old CPI and the new CPI. Okay, so important thing to factor in is that the percentages are different. The old CPI was based on 100% instruction count, and now the new CPI is based on 105% CPI count. Okay, so you can see that now there's an overall increase of 8%. Okay, with this change. Okay, I think the important thing that we are trying to show you in this question is that this conversion, okay, of your multiply to the shift or to the shift and add operations, this conversion is actually done by the compiler. Okay, so if your compiler is good, okay, is smart, it is able to do optimization for you that actually improves the overall performance of your code. So you can see that in this module, we are trying to expose you to a lot of different aspects of software development that is beyond just what you see at the application layer. Okay, so there are a lot of things in the background that actually affect the performance. Okay, things like your cache design, the way you arrange your memory structure, okay, the kind of compiler that you use, the compiler settings that you can play around with. Okay, so there are a lot of there are a lot of factors that affect how your overall code is going to perform. Okay, so this is one of the main objectives of this course, to make sure you are exposed to all these types of concepts. Okay, so this with this question we wrap up this tutorial. So I'll see you all soon for the next tutorial. Okay, thank you.